In this short video, I'll be presenting multi-alpha soft actor-critic, overcoming stochastic biases in maximum entropy reinforcement learning. This is joint work with Swapnil Pandey, Siddharth Venkatraman, and Jeff Schneider. Real-world robotics tasks can be highly complex. Deep reinforcement learning, or DRL, provides a data-driven framework to automatically learn effective policies in a variety of important robotic control settings. Notably, from surgical robotics to dense urban self-driving, optimal behavior is often characterized by precise decision-making. In this work, we show how some of the most common DRL algorithms are ill-suited to these high-precision tasks, and propose a simple algorithm to address this problem. In particular, since its introduction in 2018, Soft Actor-Critic, or SAC, remains as one of the most popular general-purpose DRL algorithms. Roughly speaking, the SAC objective incentivizes the agent to maximize a balance of extrinsic environment rewards and policy entropy, with the exact balance controlled by a parameter alpha. Although the stochasticity arising from the maximum entropy objective is desirable from exploration and robustness perspectives, in this work we show how the max-ent objective can also introduce a significant bias away from optimal decision-making, which often requires near-deterministic behavior for high-precision tasks. We also show how this bias cannot be mitigated by naively reducing alpha, as doing so forgoes the benefits of the max-ent formalism. More specifically, when optimizing the max-ent RL objective, as alpha increases from 0, the extrinsic rewards of the resulting soft optimal policy, shown in red, decrease from their optimal value. Meanwhile, the policy entropy shown in blue follows the opposite trend, increasing to the maximum possible entropy value with increasing alpha. To illustrate the stochastic bias, we study the toy hop MDP. In toy hop, the agent repeatedly chooses a hop direction and distance with a maximum hop distance of delta max. The reward is simply the magnitude of the agent's distance from the start state along the x-axis. The optimal policy is to hop a distance of delta max directly along the x-axis. The figure on top shows the state visitation distributions of 3 different soft optimal policies with 3 different values of alpha. Note that increasing alpha has 2 effects on the visitation distribution. The entropy increases and the mean hop length decreases from the maximum allowable hop length. Importantly, the effect of the hop length persists even in the bottom figure, which shows the visitation distributions of the same 3 policies during evaluation. Although the stochasticity has been disabled by acting according to the policy mean, the agents are effectively acting in vain anticipation of future stochasticity, biasing behavior away from true optimality. This raises a natural question: how can we reap the benefits of stochasticity without suffering the leftover bias during evaluation? Our answer to this question is multi-alpha soft actor-critic, or MAS for short. MAS generalizes SAC by treating alpha as a random variable. Our main idea is to allow alpha to take on a range of values throughout learning instead of requiring alpha to be some constant. The red highlighting in the pseudocode shows the only differences between MAS and SAC. At each time step during exploration, we sample a random alpha, which we then condition on with our policy. During training, we again sample random alphas when constructing the critic targets, and we again condition the policy and critic on the sampled alpha. The result is an algorithm that jointly learns a family of soft optimal policies for a range of alphas. We show how MAS overcomes the stochastic bias in the toy hop MDP while maintaining exploration efficiency of the original SAC algorithm. In the figure on the right, each blue curve shows the evaluation return averaged over 10 training seeds of SAC for different values of alpha. Each red curve shows the evaluation return for MAS for different choices of alpha distribution. Note that all variants of MAS rapidly converge to the optimal policy, while all variants of SAC clearly demonstrate the stochastic bias. Note also that the choice of alpha in SAC not only determines the strength of the stochastic bias, but also the speed of learning. We observe a similar trend in more complex robotic manipulation tasks using the Panda gym environment. Here we see that all variants of MAS rapidly recover the optimal deterministic policy. Meanwhile, for SAC, high values of alpha enable fast learning at the cost of introducing a significant stochastic bias, while lower values of alpha reduce the stochastic bias at the cost of significantly slower learning. We additionally provide results in the Carla Urban Driving Simulator. We note that the environment provides harsh penalties for lane deviations, which increases the need for high-precision control when attempting to turn corners at high speeds. We show that MAS achieves faster driving when navigating sharp turns at speed compared to the best variant of SAC tuned over a comparable range of alpha. We provide additional results on Mujoko, Panda, and Carla environments in the paper, including comparisons with variants of SAC that adapt alpha dynamically throughout training. In summary, our work highlights the value of treating alpha as a random variable in maxent RL.